So welcome everybody. It is a great pleasure to have with us here today Dimitrios Tanoglidis from the University of Chicago. Um, Dimitris is a distinguished alumnus of the University of Crete. He did his bachelor's degree in physics here and also his master's degree in our advanced physics program before he moved to the United States, where he had offers from various um, prestigious universities to continue there for a PhD. And he chose to go to the University of Chicago, given that his research interests were very much in cosmology. And he has been there. He's a member of the Dark Energy Survey, leading the search for low surface brightness galaxies, which is the topic he's going to discuss today. And recently his interests have shifted towards applications of machine learning in the analysis of survey data, which I'm hoping he's also going to tell us a bit about. So without any further ado, Dimitris, the floor is yours.
Thank you very much. So thanks for the invitation. It's a really great pleasure to be back, although this is in a virtual setting, but it is what it is. So thank you very much. So let's start. So to break the ice, this is the condition really close to my house. I took this photo yesterday. So don't complain about cold in Crete. There is no cold in Crete ever. Okay, so let's start about low surface brightness galaxies and start with a Wikipedia style definition, actually quoting Wikipedia. So low surface brightness galaxies are diffuse galaxies that have a surface brightness that is at least one magnitude fainter than the ambient dark sky. You can see the magnitude of the sky. And so we are interested in objects that are more than 5 times fainter than that. And if you are curious, like, so how do we see them? We are talking about brightnesses that are above that, so above the dark sky. So, and they are interesting for various reasons. First of all, these are difficult to detect by definition. And then, because of that, they're difficult to study over a wide sky area and in different environments. For example, most searches for them were targeted in specific galaxy clusters, but we haven't studied them that much in different environments like clusters versus field. Uh, for that reasons, we haven't tested models of galaxy formation and the connection between galaxies and halos in that regime. And furthermore, there has been a renewed interest in a specific class of low surface brightness galaxies called ultra diffuse galaxies that are defined as low surface brightness galaxies with large physical sizes. So I gave you a summary of the LSBG research, and I'm going to elaborate on that and split the talk into 3 parts. Talk about the past, although past, I mean till really recently and everything that's not our work, and then switch over to the present state, so pretty much our work, and discuss a little bit about the future. Okay, let's start discussing the past. So this type of galaxies was first theorized in 1976, that like there are galaxies, there are many of them that are below the dark sky threshold. And they were first discovered in 1986 by this astronomer called Malin. And you can see this first LSBG that was discovered. It's called Malin 1, and I think it's the largest spiral galaxy known today. It's like 3 times as large as the Milky Way galaxy. Again, so why is this interesting? Because the low surface brightness regime is largely unexplored because of the technical challenges. And although some observations and some theoretical arguments say that this regime of very small halo masses should be dominated by such galaxies, We haven't tested actually galaxy formation or the or as it is known, the galaxy halo connection in that regime that connects the mass of the galaxy, so the stellar mass, to the mass of the dark matter halos they live in. So it would be good to have to start exploring this regime and have large populations of these type of galaxies. And as I said, there has been a renewed interest in a special class of LSBGs called ultra diffuse galaxies that are pretty much LSBGs that with large physical radii. Why? Because you can see this theme here, and this is interesting that they found many of these galaxies, and they sparked this interest using pretty much this camera that was made by things that you can buy online and assemble this thing, this telephoto array. So they found many types of this galaxy in the Coma cluster. And the interesting thing about them is that they had sizes comparable to the Milky Way, but with a stellar content 1,000 times less than the Milky Way. And why is that a problem? It's because most of them, as I said, were close to galaxy centers, and they had no signs of any tidal effects. And by using stellar kinematics, they were able to say, okay, these have really high halo masses, but in such large halo masses, they should have been much more effective in creating stars. So it looks like being failed galaxies like that. They violate how we expect the galaxy formation theory to work. Um, Although some other observations have suggested that these are not failed galaxies; they are pretty much normal dwarf galaxies that, for some reasons, have very high spins and they are very large, although they inhibit in halo sizes of the expected size. So this is another argument about why this low surface brightness galaxy research is interesting. And let's discuss the state of the art before my work, before our work, in searches for low surface brightness galaxies in wide field surveys. So in surveys that in experiments, surveys that look over large areas of the sky. So using the first 200 square degrees from the Hyper Supreme Cam, Greco et al. In 2018 were able to find 781 LSBGs. You can see the distribution of them in red and blue. They separated in red and blue galaxies. You can see them in different sky patches here. So they had some signs of spatial clustering, but nothing conclusive. And also they showed that these have different morphologies based on their color. So from this slide, please keep the number, because I will show you how our work increased this number. And also keep the open questions. For example, if these galaxies actually have different spatial clustering based on their color, and yeah, pretty much this thing. And just have this in mind. I will refer to it a couple of times in the future. Okay, let's discuss the present. And by present, I mean the discovery of low surface brightness galaxies in the dark energy survey. So before going to the low surface brightness galaxies, let's discuss the dark energy survey itself. I think it's an exciting survey. It's an exciting experiment. It's an optical and near infrared survey, so it looks in the optical wavelengths, and was performed using the 4-meter Blanco telescope in the Cerro Tololo in Chile. Is the same telescope that was used to measure the supernovae that people used 20-something years ago to discover the accelerating expansion of the universe. So it's the same, follows the same tradition. So it has a 5,000 square degrees footprint. Footprint, I mean the observing area. You can see it here. Also have this figure in your minds, because it will you will see this tank shape again and again. So to have a sense of what it means, it's like this area in the southern hemisphere that DS observes, and has these weird shapes for observational reasons. For example, here I think it was a special place where they had more information. It's called Stripe 82, I think some distance information, I'm not sure. And also they wanted to cover part of what the South Pole telescope observes. So they ended up having this weird shape called the tongue. It's a photometric survey. So that means pretty much that you don't have redshift information, accurate redshift information, or in other words, you don't know the distances of the objects that you measure with great accuracy, and especially when talking about objects that are nearby. So this can be a problem, and it is a problem that I will discuss in a while. And the observations were completed 2 years ago now. So they spent 6 years observing. They measured more than 300 million objects, galaxies, stars, etc. But the analysis is still going. So now I think these days, like they release the first 3 years of the analysis. So, and after that we'll have full analysis of the survey. So the data are still being processed, although the survey is completed. Um, oops, there should be, okay, there is. Okay, so what is the science that people do, not me, with DS? So I'm rerouting a little bit to discuss briefly about the exciting cosmology results from the dark energy survey before going to the galaxy side. So the main purpose of the dark energy survey anyway was to try to constrain the cosmological parameters, and as you can see here, the constraints on the total matter content and the total amplitude of fluctuations in the early universe that is being performed by actually measuring the statistical properties of the distributions of these hundreds of millions of galaxies, like galaxy clustering, how they are closer together in space, and something else that's called weak lensing. Pretty much is something amazing. It's the fact that foreground galaxies have their shapes slightly aligned because of the background galaxies have their shapes slightly aligned because of the gravitational presence of foreground galaxies. And it's amazing that this tiny signal can be measured, and using these things can measure the cosmological parameters, but also create such amazing maps. Like this is a map of the distribution of matter in the universe, not of galaxies, of the matter. So you are able to reconstruct the gravitational potential of dark matter. So these amazing things can be done using the dark energy survey. Um, so you can start exploring. I think even the data are available. But let's switch gears and discuss about my project, our project on discovering low surface brightness galaxies using the first 3 years of DS data. And I hope that I convinced you so far. I have convinced you that it's also an exciting science project. And it's called near field cosmology. So not the classic cosmology, near field. Okay, so I said 4 steps. Step 1, you want to select, of course, galaxies that are faint. And this is our definition of what is a faint in that case. And also you want to restrict their flux radius. So actually their radius to select pretty much quite radially extended objects in order not to have too much contamination. Some also start galaxy separation cuts because you have the full catalog that has 400 million objects, contains everything you try to contain it. So if you do that, you end up with something like 500,000 candidates. So are all these LSBGs? You would like that to be the case, but most of them are false detection. How many? 90%. What I mean false detections, you see, like in theory, each one of these photos should be centered in a galaxy, in a low-surface-brightness galaxy. But actually, there are just some small objects blended in the diffuse lights of stars and galaxies, etc., that create all kinds of problems. So what to do about that? So something that is commonly used in such cases is like, okay, since I have two classes, I have LSBGs in my sample, and I have artifacts. Let's try to use what is very popular today, machine learning. However, to perform such a classification, you need usually, I mean, there are cases where you don't need that, but they're not so accurate and not very convenient for our case. You need a training set. So pretty much you want a sample of the type of objects that you want to classify, but we didn't have such a sample. So our solution was to visually inspect everything pretty much in seven randomly selected areas on the footprint of the survey, find all the objects there, both the artifacts and the LSBGs, and train a machine learning classifier to perform that. I will discuss more about machine learning later on. Pretty much, this is kind of a simple machine learning classifier, which means takes a bunch of properties, like as you can see here, the radii of the objects, the surface brightnesses, the colors, etc., and gives you a label of this is a galaxy or this is an artifact. So if you do that and you tweak a little bit the classifier, you can get one that gives a very small number of false negatives. So you don't miss many. So from all these that you want to discover, you are going to lose something by using this step. You are not going to find all of them, but you are not going to miss many, like less than 10%. On the other hand, the purity of the sample will be low. Like, from those classified as galaxies, half of them will not be galaxies. This is the predictions on a test set. So you know that. But this is not a huge problem, because if you are able to go from 500,000 candidates to, as I say here, 44,000, 45,000 candidates, then it's okay. You can start visual inspecting. And yeah, at some point I spent a whole summer actually visually inspecting galaxies and it's rejecting remaining false positives to end up with a final catalog of 20, almost 25 galaxies. And it was painful. So you can see here, you have all the candidates and you check, yeah, no, yes, no, yes, no. And the final step was further galaxy modeling and also correcting for the galactic extinction, like actually the presence of some foreground dust. Some people may be interested in that. That changes the magnitudes that you see, so some things may appear fainter than they are, etc. So if you do these final corrections, you end up with a final catalog of almost 24,000 LSBGs. So I hope you appreciate the previous stage in galaxy surveys was a catalog of 781 LSBGs, and we went up to 24,000 LSBGs, radially extended, large ones. And let's discuss now a little bit this catalog. Again, similarly to what other people did, we split the total sample into red and blue galaxies by pretty much like you see that if you make a color plot, these two present a bimodal distribution. So you fit, you split them in like as you can see here, the thing that you feel natural to split them into red and blue. So you have more blue galaxies and less red galaxies. And let's see a little bit how these two populations are different. So first of all, morphologically, they differ. Red galaxies are more elliptical, while blues have signs of spiral structure. These blue galaxies are like more star-forming galaxies. Uh, um, Also, they slightly differ in their photometric or structural parameters. For example, blue galaxies are brighter. And then what is probably most interesting is like, okay, here is the spatial distribution of the blue sample, pretty much homogeneous. Some signs of spatial clustering. This is the distribution of the dark energy survey footprint, but pretty much homogeneous. Then you check the distribution of red galaxies. Totally different story. So super clustered. Um, these are older galaxies that have probably time to fall to fall into galaxy clusters. So this is very interesting to see this difference in the clustering patterns of the two types of galaxies. Okay, you can formalize this and like say, okay, actually what I see, I can formalize it in terms of the 2-point correlation function and actually measure and quantify how much more cluster is the red sample. And you create this that pretty much measures how this clustering changes as a function of the angular size. So pretty much in all scales, red galaxies cluster more. And also you can compare with normal galaxies and see how these, like how the clustering is different between normal galaxies and faint galaxies. So I select here a sample from the DS data, but of higher surface brightness, and also another galaxy sample from an external catalog with similar distributions. And you can see here again this function that shows you the clustering of normal and low surface brightness galaxies. So they have some interesting differences. In some scales, the clustering is pretty similar, except here in very small angular scales where there is this suppression of the clustering of LSBGs. So we are not sure if that's an observational effect, something that we have missed galaxies that are close to the centers of clusters, or it shows you that actually LSBGs do not form at the same rate in centers of galaxies. It's an interesting observation. We don't make any bold statements, but it's certainly interesting that we see different clustering properties between normal galaxies and LSBGs. Okay, and then you saw that you have these overdensities, and I discussed about clustering, but focus on clusters. So these overdensities that you see, these places that have more LSBGs, are they associated with known normal galaxy clusters as we know them and love them? So what we did here was to create a density map and find the most prominent peaks, so the peaks that they're having a density more than 5 sigma above the mean, and associate them with known clusters, groups, and large galaxies that may have around them LSBGs. And this is interesting for some reasons. First of all, to see if there is a one-to-one association, but also because this provides distance information. Because, as I said, we don't have accurate distance information for these galaxies. If you are able to associate at least some of them with galaxies, with known galaxy clusters, you know the distance to them, and you can measure sizes. And I will show you why this is interesting. So, yeah, we did that. We associated them. Many of them were associated with Abel clusters. Some of them with NGC galaxies. Some of them with reflex clusters, and some of them didn't have associations at all. That may be interesting. So you can see here some faint galaxies that somewhere here are the LSBGs close to this NGC. Here is a galaxy cluster. I don't know where is the LSBGs. But here, for example, there was an overdensity of LSBGs, but you cannot see any visible galaxy cluster. So this may be an interesting case. Again, not bold statements, but something for further exploration. Um, and an application, as I said, this process allows you to get some distance information by assuming that everything that in projection is actually at the same distance as the galaxy cluster. You can get the physical sizes of the LSBGs by knowing their distance and construct a size luminosity relationship. So size, physical size in parsecs versus the absolute magnitude of these galaxies, and project your sample versus other samples from other surveys. And also here is the limit for UDGs, and you can see based on the definition of ultra diffuse galaxies where they lie. And what we find is that pretty much under these assumptions, these are just a natural continuation of the total dwarf population of galaxies. They are not in a in a special class in the distribution of properties. These these UDGs are just like a natural limit of the low surface brightness galaxy population. Like they are super, like they lie where they should. Nothing. They do not occupy a special place on their own. Okay. I don't know if I should take any questions or wait the end, but I assume that there are no questions. And let's move on to the future after our work. So what the future is going to bring into the survey science and LSBGs. So the next big thing in cosmology, in low surface brightness galaxy science, pretty much in everything, is the upcoming legacy survey for space and time on the Vera C. Rubin Observatory. You have to write the whole thing every time you mention that. Um, which I think is going to start operating this year, or at least that's the idea. I don't know if things have changed. This is going to to map an area of 20,000 square degrees, so 4 times that of the dark energy survey. Again, it's an optical survey, deeper, and it's going to produce 20 terabytes of data per night. So it's projected to measure 20 billion galaxies after 10 years of observations. So these are really big data, not just because it's a sexy name. It is a big data case. So in such a case, we would have to rely on visual inspection as we did for BES. For the same case, of course, this is not going to be feasible. So let's discuss a bit about deep neural networks and how you can use them for astronomy. There are, in my opinion, 3 levels of how you can use machine learning in astronomy. One is to redo things that are well understood and without adding much, but use machine learning because this is what people do. Second is to solve problems that are meaningfully to be solved using machine learning. I think this lies in this. And in the third category is like try to advance both machine learning and astronomy at the same time. I haven't done that, but that's my future goal where I target. A specific class of neural networks are known as convolutional neural networks, are inspired by how our eye works. So it gets an image. So they work directly at the image level. You don't have to provide galaxy or object properties as we did earlier in the machine learning classifier. So you just give to that classifier raw images, and it actually works like our eye. So it has many connections from the image to a layer of neurons, and then that goes to another layer that constructs more abstract images, and so on and so on. And in the final stage, it classifies between the classes that you give it, and has some interesting applications in astronomy, separating stars with galaxies, finding strong lenses, finding merging galaxies, and many other things. However, such an approach, in order to work, requires a large number of labeled uh, examples. But we just created one because of our painful visual inspection. So we have a large one, so ideal to test machine learning classification. So I will discuss with about this work that we recently published. Actually, it was recently, it got accepted recently, where we used a simple convolutional neural network, a simple architecture, a simple configuration of neurons, to test if that can perform well in classifying LSBGs versus artifacts. I remind you that using machine learning, half of those classified as galaxies were still junk. So we have a large training set. So we randomly selected 20,000 from each category. You can see examples of LSBGs and artifacts. Here, as it is common, we split into training, validation, and test sets to test the performance of the classifier. And I can show you some results of that, how this deep shadows classifier, this deep learning classifier performs, and how it performs compared to other machine learning classifiers on the same set of galaxies. Machine learning classifiers using properties and not their images, so it overperforms. This gives you actually the number of false positives versus the number of true positives. So the upper, the more this thing goes to the upper corner, means it's better. And you can see the comparison here. So it has an overall accuracy of 92%. And completeness of 94%, which means that you are going to lose less than 6% of your galaxies. It has a purity of more than 90%, which again means that from all those you find, less than 10% will be junk. Although this is not the whole story, I will show you in a moment that it may be that the actual results may be better than this number actually. And I will show you why. Okay, so yeah, here are the examples of what the algorithm actually sees, and you can see true negatives, false negatives, true positives, and false positives case according to our label. So this says this is true negative and true positive related to what we have labeled them, like how we have labeled them, but we were not perfect at all because we had to inspect many galaxies. So we certainly had some misclassifications there. And the interesting thing is that the neural network was able to correctly classify and correct us, because you can see these here are classified as false positives. So it says, like, according to our label, these are classified as galaxies, but they are not. But if you look at them, they are galaxies. So these are probably cases of mislabeling, of the algorithm correcting us. And in other cases, you can see pretty much that if the image is dominated by one central galaxy, it's classified positively, and if it has a lot of other features around, is classified as negative. So this shows you how the algorithm thinks. Okay, so now the interesting part, because okay, there are many things out there where people use a data set and they split it into training and test sets, and they say, oh, I trained an algorithm and I have this performance of my on my test set, and I have managed to create an algorithm that performs better than human eyes, and then, oh wow, I will use this to find something else. Yeah, this usually doesn't work, because when you want to take something trained on one data set and try to use it in another data set, the performance usually falls by a lot, and it's not feasible. So what we did here was to try to test if our classifier can find LSBGs using data from another survey. We didn't have many other surveys, but we had these 700 galaxies that I discussed at the beginning from the other survey. So we also asked to give us their artifacts that they had also rejected through visual inspection. So we did two things. First, we took the classifier trained on data from the dark energy survey and went on to classify these from the other survey without anything else, without tweaking the algorithm at all. That resulted into an accuracy of 82%, so lower than when both training and testing is performed on DS, but quite good. A precision of 85% and completeness of something like 80%. Not great, but quite good. And then you just retrain the algorithm using a tiny set, like 300 galaxies, 300 total examples, both galaxies and artifacts, from this new survey, just a tiny sample for for deep learning applications. And this improves the results by a lot. So improves the accuracy from 82 to 88%, but more importantly, it improves the completeness, so how well you find everything there from 80% to 94%. Uh, so this shows you that, first of all, things can be improved by doing this transfer learning, so tweaking a little bit the data, but also shows you that this is a very promising way for future surveys, because using our sample that is large enough and probably a tiny um, sample from, let's say, LSST that can be visually inspecting, to, you can tune your algorithm to to this new survey and use it to find galaxies in that new survey easily, without having to inspect thousands of them for a training set, or without having to inspect all of them using visual inspection to find them. And yeah, here we tested a little bit how robust are these results, the accuracy scores. They are pretty robust. So the accuracy overall is from 91 to 93%. So this is by bootstrapping. So actually classifying random subsamples. I should skip a little bit these details. Also, we tested um, how sensitive are the results in the way you split your data set into training, validation, and test sets. The conclusion is these results that I showed you are pretty robust, and also they are robust in label noise. Um, so I showed you that we had some misclassifications, and this may affect the performance. No, unless we had done something crazy, like misclassifying 1/3 of them. The results are pretty robust. This is a property of neural networks in general. Generally, they are quite robust in label noise, in mislabeling of the training set. Um, okay, so this concludes this discussion of the future and how to use convolutional neural networks to find LSBGs. I wanted to show you a little bit what I'm working on right now. It's like super fresh off the boat. In this one, it's an algorithm for object detection that hasn't been used that much in astrophysics, but I think holds great promise in many areas. In that case, not just um, classifying images, like saying in these images there is something versus there is not, but actually finding where something is. So these are the focal planes of the dark energy survey. And you can see in some cases, you have these that are called ghosting artifacts. These are reflections pretty much from starlight of the like of the camera itself. You can see here is a camera actually that is reflected, and you would like to remove them, but with at the same time keeping the good part of what the camera sees. So here we use an algorithm that was actually developed by Facebook to find images, to find your ex, to find people. But we use it to find these ghosting artifacts, and it surprisingly for how challenging this thing is able to detect them fairly well. This is super preliminary. And it's also related to the low surface brightness universe because these things are kind of noise for low surface brightness searches for low surface brightness science. And I think that kind of concludes my talk. Yeah, of course, we have discussed a little bit about future directions. So, in the whole discussion about ISBGs, etc., one challenge is to find ways to accurately measure the distances, especially when discussing in photometric surveys that you don't have redshifts. Estimate their mass using weak lensing, check these galaxy clusters that they don't have counterparts, compare with theory. In theory, that's why we give this catalog to the world, and I know that there are people that have now used it, are using that. Yeah, find distances, etc. So my conclusion is that the future is generally faint. So there's a lot of work that can be done. By the way, my catalog is available, so you can find it. Even people that want to start playing with it, it's very easily accessible. Um, so this was a great collaboration. There are many more than those people here. These are my main collaborators, like my advisor, Alex, and many other people from different universities working on these areas. Like that's a good thing about surveys. You get to collaborate with many people, and I want to thank all of them. So thank you, Ευχαριστώ, for the invitation. Um, Okay, I think I
Thank
was
you
good
very
in
much,
terms of
Dimitri.
time.
You are perfect. Thank you very much for staying
Thank you.
in
And I will
time.
hope to get some non very harsh questions. So these are hands. Like when I see some hands, means
Yes,
that
yes.
okay.
Rafael, so please go ahead.
Γεια σου, Dimitri. Thank you very much.
Yeah, sure, Rafael. So are we continuing in English?
Yes,
Yeah.
please.
Okay.
Thank you very much. It was a
Thank
very
you.
interesting talk and nice work.
Thanks.
I have a simple question because you mentioned a future mission,
Yes.
and I want to ask you how much do you expect that this new data will improve the amount of these low surface brightness galaxies?
You mean improved by what? By
By the number.
I don't know.
Do you have? Can you estimate how?
I think
Depending on the.
this is going to be deeper. I mean, certainly it's going to be at least 4 times more because of just of the area, at least. But this is much deeper. I don't have a projection, to be honest. So, yeah, I think it's hard to estimate because, like, for example, one could say something about the difference in depth, but these are point source estimates. Yeah, I mean, I haven't done this projection. I don't know if there is a way to project, like, in an analytical way. I mean, probably there are people doing simulations, like you can simulate them in LSST and see how well you retrieve, but no, I haven't done that.
Okay,
So
I mean, even if you have an approximate number, it's okay.
Well, I mean, so the other thing you can do is scale the number of galaxies, and of course they have different distributions. But I don't think you can lose something. You can maybe get more. So if you divide the 20 billion galaxies over the 300 million galaxies of the galaxy of the dark energy survey, you get a number, and I suppose you can multiply this by the number we found in DES. But yeah, I don't have a projection for that, and I don't know Yeah, I don't know if there is a way to get a projection. Sorry.
Okay, thanks.
Nico?
Γεια σου, Δημήτρη. Very nice.
Yeah.
Talk.
Hello.
I have basically a couple of questions, technical questions on machine learning.
All right, I'm happy about that. I prefer those over the galaxy questions, to be honest.
So I wanted to ask you, were your images small enough to do this? Or if they were big, how did you deal with a computational problem? I mean, resources.
Big and large. So what do you mean? So so each one was 64 by 64 pixels, if you are asking that. The total, I mean, if you want the total data, that the data set was something like 4 gigabytes.
No, I'm just asking about the individual images, because I know, for example, if they are more than 500 by 500, you may have.
Okay, so this is related to how much detail you want. Yeah, we tried to scale it down, although I didn't check if higher resolution would give better results. But pretty much I was able to see that if you have 64 by 64 pixels, it's easy for a human eye to see the differences of LHBGs versus artifacts. It was not like that you were getting more information, at least for a human eye, by having a higher resolution. So yeah, I used this resolution pretty much because I wanted to have a smaller data set in terms of size in gigabytes. But you said like 500, I don't know, like now I'm working with these images here, and these are 400 by 400, and this is a much more challenging problem, and I think it works fine. So I don't know what's the size of, like, I haven't heard actually that at some pixel size this thing breaks down. I suppose we need more space.
In terms of computing time, for example, and resources. That
I mean, then it depends on your resources. So I have used Google Colab. I don't know, like I kind of suggest it. Actually, I used the Colab Pro. I think it's not available in outside the US, where you can get a lot of space and GPUs and a lot of RAM memory. So yeah, I think a lot of RAM memory, etc. So you have a very powerful machine. But then, if that was not working, you can use a cluster somewhere. I don't like clusters that much because I'm technophobe, as Vaso knows. So I don't want to start connecting with SSH, etc. But anyway, I suppose there is a solution if there is such a problem. But it was not a problem in my case.
Okay, I see. And a second question, if I may.
Yeah.
So you said there were cases when the algorithm corrected actually the human eye.
Yeah.
And I wanted to ask you, in order to find all of these cases where the model would correct you, do you have to run it multiple times with different splitting? Because
no,
it cannot find it on the training set, right?
I haven't tested. I suppose it was able. So, but I mean, I suppose if you train on the training set with the with this small number of misclassifications, and then use to get labels for the same training set, it will probably do that. Since it did that on the test set, I suppose it will do it on the training set as well. I haven't tested because, I mean, anyway, I haven't tested about misclassification. That was just an outcome of checking what are the false positives and the true positives, and just saying, okay, these false positives do not look actually like false positives. But I haven't checked all of them because, I mean, in order to check all of the corrections, I have to check all of the images again. But I suspect that it will do that, the same thing on the training set as well. Maybe not at the same level, because when you train on something, it tends to adapt more to that, has kind of overfitting. But I suppose that it will correct on the training set too.
Thank you, Dimitri.
Thanks.
Giorgo?
Yes, Dimitri.
Yeah, we are
Uh,
co-authors, right?
sorry?
We are co-authors, right?
Yes, we are co-authors.
Okay.
And I'm
Haven't
glad
talked to you.
that. Yeah, we haven't talked in a while.
Yeah.
I would like to ask you, at some point you talked about using LSGBs to determine distances. So I
Not to
guess,
determine distances. We don't have their distances. We would like them to have them.
yeah, I would like you because I lost the discussion at that point. What I understood from the bits that I managed to understand was that you can use, for example, for LGBs that are classified as red, given that they lie at the centers of clusters, naturally,
Yes.
you can use them in order to specify the distance of the cluster. That's what I understood.
No, the
Even
opposite. I
from the
mean,
distance of the cluster, you
yeah, because we don't have reliable distance information. I mean, not at all, let's say. For this, no, because by the way, I have selected radially extended LSBGs in order, pretty much in order not to have too much noise. And by selecting radially extended, you are pretty much bound, first of all, to select nearby objects.
okay.
Because if they are not, if they are distant, objects will not pass your angular selection. Then for nearby objects, these techniques that these surveys have in order to estimate distances totally break down. Like they give nonsense. Total, like negative distances, to give you a sense. So then you can just assume that, which is not totally correct, that, for example, everything that lies within half a degree from Fornax cluster, for example, lies at the Fornax, is at the Fornax cluster. So you know the distance to Fornax. It's 18 megaparsecs, I think. And you assume, which is not totally correct because it's in projection. So you're talking like near to Fornax in terms of angular distance, but you don't know what's going on. Um, I have something like that. Sorry. Anyway, you can say that those that are within half a degree from the center of the cluster, they are. Sorry, someone said something. Anyway, so everything that is within half a degree is 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 at the same distance, and you can do other things like find their sizes.
So you mean find the size
Of
of
the
the
galaxies, not of
of
the
the
clusters, of the
okay,
galaxies.
okay.
The
So
physical sizes, because you have the angular sizes, but you may want to go from angular sizes to physical sizes,
okay,
to parsecs, pretty much.
okay, I see. Thanks.
So you do this like for these galaxies. If I hadn't made this assumption, so these are for like taking everything within the 10 most prominent peaks. So as you can see
Sorry,
here,
this on the y-axis is the radius of the galaxy,
of the galaxies in
the
parsecs.
physical radius, not the
Yeah,
projection.
the physical side, assuming that everything within half a degree of the cluster is in that cluster, which is an assumption, not wonderful, probably, because some of them will be just randomly in projection there. But anyway.
We have a question from Vincent, and he asks, what is the effect of galactic extinction on the power spectrum that you derived from the low surface brightness galaxies?
Well, those that I showed are corrected for the extinction. So there should be nothing because they have been corrected. I don't know if there is any effect in the selection process, because at some point I showed you that we went like from 425 5,000 galaxies to where is that? So yeah, we're like 24 something, and we rejected something like 1,000. I don't know. Should this thing affect it somehow? Since anyway, those that we have are corrected. I suppose no. I cannot see if there is a selection effect. But anyway, the final thing, like everything here is for a corrected extinction. I'm not sure, like if it is no, if the permutation of the operation, like first correcting for extinction and then calculating this, it's the same as first calculating and then correcting or something. I'm not sure, but for sure this is corrected for extinction in terms like everything here has been corrected. But yeah, I'm happy if you have. I don't know if they do that.
So
If obscured by dust, I don't know if that's the same thing. So if it's obscured, yeah, if it is obscured, it means that it's actually brighter, and you see it fainter, and then you have corrected. Is this the same thing? Because yeah, we may miss at the other end, I suppose, but pretty much okay. So in terms, yeah, maybe, but this is goes down to the kind of the completeness of the survey. So I can see that you can miss some of them in that faint end. So this goes like down of the observational limit of your survey, but I don't know how many of them there could be. So pretty much you lose those that are extremely faint, and they become even fainter because of extinction, and they go below the limit of what the survey can detect. Interesting. There shouldn't be many.
Nikki Lafis has a question.
Yes, Dimitri, you said, and we saw that the red galaxies are clustered.
Yeah.
And these clusters are, some of them at least, associated with known clusters. But the blue ones are not, are more or less uniform. And my question is, why did the existing clusters did not attract some of them to force them to cluster?
I think these are younger. So my understanding is that like is where they form. So if they form in the field and they are younger galaxies, they didn't have the time to fall into the clusters.
Okay,
cluster that much.
Time is a crucial parameter. If they did not have the time, but if we could estimate their life, their age of these blue galaxies, we could then kind of define a sphere of influence for the existing clusters, so that if they were found in that sphere, they would fall in.
Yeah, I mean, yeah.
So
it's interesting.
This should not be this map should not be entirely uniform, but it should be it should have some holes. I would expect if time existed around existing in the neighborhood of existing clusters.
So why this is, yeah, I'm not sure. about that.
In some other context, when we don't, I don't know if this is true for low surface brightness galaxies, Nico, but for other galaxies, my understanding is a selection bias. If something has fallen into a cluster, it tends to lose its gas due to ramp pressure stripping and things like that. So you cannot form new stars, and that's why you see it redder. But I don't know if this is the, so it's an observational bias, but I don't know if this is the case here. I don't know if it transfers.
Okay, it could. It could.
But I presume one of the arguments of Nick is that if these are all filled galaxies, right, and you would have uniform distribution of filled galaxies, then you would expect that in areas where clusters exist, that low surface brightness galaxies would be affected by those, and if the two populations red, and if it's passive evolution for the reds, then you would see the holes that Nick suggested, right?
Yeah, but in 3 dimensions, clusters don't have such a large filling fraction, right? I mean, you have things that are below, in front and behind. So if you just take out the cluster, I don't think it would leave in 2D projection such a big hole.
That's a good point. Yeah, that's a good point. That's a good point. So statistically, you may not be able to see that. Yeah. Okay.
Okay, I have a question more on the implications of the plot you showed, Dimitri, on the size versus what was it? Some mass. Yes, this one.
Magnitude.
So the fact that you basically just see this continuation, doesn't this answer the question of whether these live in whether these are basically failed galaxies in big halos? It looks like, in fact, they are not, right? If they
I think
if they walk like a duck and quack like a duck, it looks like they're dwarf galaxies, right?
So I think the consensus, of the record, I think the consensus is that these are normal galaxies. At some point, this team at Yale claimed otherwise and sparked the discussion. And then everyone else since then has said, oh, no, they're fine galaxies, but they're still interested. Pretty much everyone has said that these are normal galaxies, not failed ones.
Yeah, okay. Any other questions for Dimitri? All right. If there are no other questions, and since it is time that some of the people will start going to their next class, let us thank Dimitri very much once more.
You.
Thank
For
you.
the invitation.